welcome back to the second video on part 2 of 2D projectile motion. This video, I'm going to finish up these rest of the questions on the other side of the page. Okay, so after you flip this page over, your table should be reproduced on this side, and because we're going to continue to use the same table for all of these questions. And here is the table. Okay, so now we have the table reproduced and we're gonna do C. C is asking for the maximum height that the spoon reaches. So it's looking at, if we go back to this drawing over here, this question is looking at this height, this maximum height. So we're actually going to look at the vertical components instead. If we take a look at the vertical to 1D problem, then we have just finding the maximum height as you do always. So looking at the vertical components only. So we scroll back to over here, and we're only, again, going to be dealing with this vertical side. Now, here's the other thing. When the object reaches maximum height, very similar to the other problem, we know that specifically in this case, the final velocity is 0. We also technically know the time, which is approximately 10 something seconds from the previous question. I would rather use my original values that were given in the problem or I found earlier rather than calculate it later, just to avoid any sort of error carried over issues. So I'm going to use U, A, V, and S. And going back to our 4 kinematics equations, the one that is going to work will be the following. And the one I'm going to use is going to be V squared equals to U squared plus 2AS. 2 S's. Okay, so now we're going to substitute in our values. We know that the final velocity is 0. This can go away, make our lives easier. And then we're going to solve for S. So let's solve for S. Move U squared to the other side. We get negative U squared equals to 2AS. Dividing both sides by 2A to get S is equal to negative U squared over 2A. And then U then becomes, that's the initial one. So look again, we're looking at the vertical components only. Vertical components have negative 102.394 meters per second, and all of this squared divided by 2A, and then A is negative 9.81 meters per second squared. And solving for this S should give us about 530 meters as our maximum height. Next one is looking at what is the velocity of the spoon when it is at its maximum height. Suspicious. So if we go to the, actually this is very funny because you don't even have to do any calculations. Why? Let's go up to the top. Take a look at our little drawing and take a look at the other drawing. Notice that our at the maximum height, Vy is 0. Vy is 0, which means the maximum height, the only velocity there is that horizontal piece. And we know that the x component of our velocity never changes in the entire motion of the 2D projectile, entire trip. So in fact, we don't even have to solve this. The velocity at the maximum height is Vx, which is 71.697 rounded up to 72 meters per second. And of course, you would have to include a reason because Vy equals 0 and Ux is constant. Okay, and then right below we have a little notice. Notice how the horizontal velocity doesn't change since there is no acceleration in the x direction. Phew, that was easy. Didn't have to do much there for calculation at least. Now we're on to E. What is the time of flight of my spoon? So there's actually 2 ways you can do this. 2 ways you can think of this. If you go back to one of our previous problems we solved, we found the time it took the object to reach the maximum height, which is 10 seconds. So if we take a look on a 2D projectile, we found this time. Okay, the time it took for it to go up. And based on symmetry, whatever time it takes the object to go up, it will be the same time it takes the object to come down. which means the short way of doing this is taking that time from our previous problem and multiplying that by 2. So I'm actually going to have to calculate the time a little bit better over here. So let's do that first. The time we got is 10.4377. I'm going to store this value as, on my calculator, 10.4377. So that means I can just go to E and multiply that one by 2, giving me the total time. This is time to max height times 2, which is 10.4377 times 2 gives us 20.875, which rounds up to 21 seconds. I can show you another trick how to do this one as well. And that is assuming what happens if you did not find a time that it took the object to go up to the maximum height. Let's say you didn't know that was 10.4377. What could you do otherwise? I'm going to go back to my trusty little table and draw it again for this problem because some values will be different. So here's my reproduced table. Now here's something that there's a few other things we can record down here as well. If we go back to our projectile picture, 2D projectile motion picture, the object, there's a few other things we know. If the object goes up and it comes back down for us to find the time of flight, which is the entire time the object's in the air, notice that in the entire path, when the object comes down again, so going up and coming down, notice my vertical displacement hasn't changed. So that S, the displacement, in this case, is actually 0. Woo. If it goes back and comes back down to the ground, vertical displacement is 0. And in this case, we want to find the time. We also know that based on symmetry, that the final velocity is the opposite of 102. So this is negative 102.394 meters per second. So in fact, there's a few ways you can solve this problem. I'm going to just show you which equations you can use, but I'm not going to do the whole thing. Of course, you can do that yourself, knowing what the answer is now. But you have two solutions. Number one is going to be in black ink. You have initial acceleration, you have the displacement is 0, and you want to find time. So in that case, what you could use, going to your kinematics equations, you have S is equal to mu ut plus 1/2 at squared. And in this case, if S is 0, you are left with a much simpler case, because notice how if this is 0, you can cancel out a t for both terms. So then you're left with 0 is equal to u plus 1/2 at. And then you can just solve for t from there. You can do that one yourself. And then you can also do this other one, which uses final velocity, time, acceleration, and initial velocity. And this one you can use v equals to u plus at and just solve for t. So those are many ways you can do the same problem. And of course, they're all going to give you the same time, which is 21 seconds. F, last two now. What is the horizontal range covered by the spoon? What it means is how far the spoon traveled horizontally. So in this particular case, if we go back to our drawing to visualize this, it takes the object from the start all the way to the finish, and we just want this horizontal range. Which means if we have how long this object took in the air and the horizontal velocity component, we can calculate this horizontal distance. And we have exactly this. We found it in question E. We know the initial velocity, and in fact, I'm going to use the same table because it's the same problem, or the similar setup. We have the initial x component, which doesn't change, and the time that we found was 20.875, which is the same time that it takes the object to travel that horizontal range before it hits the ground. So for F is actually dealing with the x direction. And all we need to do is take ux, or to find this horizontal displacement, this is all ux times t which then gives us 71.697 ... meters per seconds times the time. Notice I'm using all non-rounded values, giving us about 1,500 meters. Last problem, G. Alrighty, this is the end. Okay, so at the very end, we want to find the final velocity of the spoon before it hits the ground. Now, we already know that based on vertical symmetry, that the initial velocity going upwards is going to be the same velocity, same speed of it, but going downwards. And we've shown that in our previous table where these two values are equal and opposite to each other. We have these two. We also have the fact that the horizontal velocity component doesn't change throughout the journey. To solve for the final velocity, notice it doesn't ask for a component, it asks for the total. If you're asked for the total, you have to put the two components together in a 2D diagram. To show that, let's draw it out. So we got a straight line, and then we have the vertical component, which is 102.394. I didn't put the negative sign because I'm already drawing the vector anyways, and I'm going to indicate the direction accordingly. And we also have the horizontal component, which is 71.697 ... meters per seconds. And the resultant velocity is our final velocity, the total. This is the one that we want. Okay, this is the one that we want. And of course, if you take a look, oh, it's just Pythagoras. If we just do the Pythagoras, we get, and after you put everything together, you will find that it is exactly 125 meters per second, which was the original velocity. Now that's not all. Let's find this angle. And finding this angle, we're going to use tan. Tan is the opposite over the adjacent, which is u here. And solving for the theta, we get, by taking the inverse tan, we get also 55 degrees. And when we write this out, we write 125 meters per second at, or whatever, or just 55 degrees below the horizontal. Below the horizontal, if you take a look, imagine this is the horizontal, going downwards from the horizontal is that degree. So notice that the final velocity is exactly the same as the initial velocity, but the direction is different. Instead of above the horizontal, it is now below the horizontal. So that is also a unique property of the symmetry in the 2D projectile motion. And that's kind of what I wanted to show you as well as an overlying theme, is that 1D projectile motion, the symmetry of 1D projectile motion, also carries over into the symmetry of 2D projectile motion. Of course, all of that breaks down if you take a look at asymmetric cases, but that's one thing you can see from behind the scenes. Also, you really want to get used to the fact that doing your calculations in 2D projectile motion involves two independent 1D problems. And where you put that in the end is the time. Time is what connects the two tables together. And in the end, we found that if we want to find any total velocity or a general vector, you must put the individual components back together, like building back the Lego blocks again. So there it is. That is the end where we put the two velocities again together. So hopefully you got something out of this video, or got a lot out of this video, hopefully, because you're going to need to use all of that to do some of the problems that I've issued below. And also keep in mind that the more practice, the better. These problems are tough. You have to put in the time to work through them and check your answers constantly to see if you're on the right track. Otherwise, thank you for watching part 1 and part 2, enduring these 2 long videos, and I'll see you back next time on the Lee channel, signing out.